The answer Einstein came up with went like this. When you shine light on the metal, energy isn't arriving in a continuous stream. It's actually arriving in packets of energy. And an electron either absorbs that packet and all of it, all in one go, or it doesn't. If it doesn't absorb it, then that packet of energy just bounces back off again. These packets of energy are what we call photons. Now this is super weird because it's like the light is behaving like particles. So instead of having a continuous wave, we've got these discrete, is the word we use, discrete particles of light. And remember, each one of these is what we call a photon. So this is wave-particle duality. The light is, in this situation, behaving like particles. The energy of each of these particles of light, these photons, is hf, where f is the frequency of the light and h is a constant called Planck's constant. And this now explains why the UV light caused photoemission, but the visible light didn't. A UV packet has enough energy to allow the electron to escape, so it absorbs it and escapes, but a visible light packet doesn't have the right amount of energy for the electron to do anything, so it doesn't absorb it. All right, and now here's a practice question to allow us to try out this idea of a particle of light, a photon, with energy hf. Okay, so first of all, we're given the wavelength and we know that light is travelling at 3 × 10⁸ meters per second. And so E is hf, but the frequency is c over lambda, and so we get that many joules. And then a quite common twist on this question is now to ask about power. So the number of photons emitted each second to produce that power. Okay, so how do we do that? Well, we remember that power is energy transferred over time. Now, we know the energy of one photon. So if we knew how many photons per second there were, then we could multiply that by the energy of one of them and we'd get the energy per second. So we can then use this. There's the power, and that's going to be equal to however many we have per second, which is the thing we're looking for, times the energy of one of them. And then working that through, you'll get that the number per second is this whacking great number, rounded to 2 significant figures right at the end.